So in this chapter, we're going to take a look at earthquakes, and we're going to start off talking about seismic. As we discussed in the previous chapter, understanding the layers inside the earth is really important, and the way that we can tell about the layers inside the earth is looking at seismic. So that's why we're going to talk about earthquakes. So our earthquakes, right, I think we have a general understanding of earthquakes, right? So when the ground shifts and shakes, right, we call that an earthquake. And as we mentioned in the last chapter, there's going to be vibrations that are produced from that earthquake. So when the plates slip past each other, right, and the energy is generated, we're going to have 4 different kinds of seismic waves that are going to be produced. And they're all produced at the same time, so I kind of want you to think of it as like when you throw a rock into the water and you get all those ripples that generate from the same spot at the same time. All 4 of these waves are going to be generated at the same time. However, they travel at slightly different speeds. And this is going to become important, as you'll see later on, as we talk about how to find where the earthquake happened. So, we can take these 4 waves and break them down into 2 groups. We have body waves and surface waves. So we're going to go through each of these 4 waves. We're going to do it in order of speed. So our fastest is our primary wave, right? The P wave. The P wave is a body wave. So body wave means we travel through the earth. So it's going through the inside of the earth. So it's fast enough that it has enough energy to penetrate all the layers inside the earth. So as this wave travels through the rock, it actually compresses and stretches the rock as it goes through, as you can see in this picture down here. I want you to pay attention to the right side of this picture. Notice all these boxes are the same size, and this would be your undisturbed rock. And as that wave passes through it, you can see right here, it's compressing, and then on either side of it, right, it's stretching it, okay? So that's important to realize, right? So as that wave travels through, it's compressing and stretching. The P wave, as I mentioned, is the fastest. Now, what's important about this is that it's fast enough that it can travel through solids, liquids, and gases. And this is going to become really important when we talk about the layers inside the earth in just a minute. What do I mean by fastest? Okay, well, you've seen those cheesy geology movies, right? When there's an earthquake, you've got that pin, right? And that pin starts going crazy, right, to tell you there's an earthquake that's happened. So that first wave that hits the seismograph is going to be your P wave. That's what I mean by the fastest. Our next wave, which is also a body wave, so we have 2 body waves, 2 surface waves. The next fastest wave is the S wave. S wave stands for secondary. It also stands for shearing. Shearing means we're taking an object and we're pulling it in 2 different directions. So this wave takes the rock and moves it both up and down, right, as you can see in this picture down here. So it's kind of that wriggling up and down motion that you probably imagine when you think of a wave, but it's moving that rock up and down. Now I said P waves are slower than S waves, so they hit that seismic paper second. Now what's also important here that I want you to keep in the back of your mind, S waves are slower, so they only have enough energy to pass through solids. They cannot pass through liquids or gases. They don't have enough energy. And this is going to be, again, important when we start talking about layers like the outer core in a few moments. Then we have our 2 surface waves. So the surface waves are really slow. They don't have enough energy to pass through the interior of the earth. Instead, they just come up to the surface, and these are the waves that really do all the damage on the surface. So the first one, which would be the 3rd fastest, right, if you're keeping track, that would be the L waves or the love waves. And you can see they move the ground back and forth, kind of like a snake. So if you ever watch the Discovery Channel or something like that, and you're looking at some earthquake shows and you see buildings moving back and forth, right, that's what you're looking at, the L wave. Then the last and slowest wave is the R waves, which are the Rayleigh waves. The Rayleigh waves are fairly complicated. You see they kind of move in a circular motion, so they move both up and down and front to back. So they're fairly complicated. So I think you can easily see why ground gets damaged, right, during earthquakes. So, as I mentioned, right, when we take a look at seismic, this is something we'll look at a little bit more in detail a little later on in the chapter, we can see our waves coming in order, right? So remember, our first wave is the P wave, okay, that's what we see there, okay? And then we're going to get our S wave, that's actually this guy right here. Okay? And then we get our Lev waves, which is probably right in here, and then our Rayleigh waves. Okay, so they're always going to come in that order. And the time distance between these are going to tell us the distance. We're going to get to that in a little bit in this chapter. Now, what's really important about these seismic waves, as I told you in the last chapter, is these seismic waves essentially act like an ultrasound for the interior of the Earth. So they can give us a view of layers and things deep down inside the Earth that we can't see because we can't dig that deep. So the P waves and the S waves are really the important waves that tell us about the interior Earth because they are the body waves, right? So that's why those are important. So the body waves definitely tell us about the core. Remember, we can sample the crust all day. We can sample the mantle through igneous rocks, but we can't sample the core. So how do we know that we have an inner and an outer core? Well, the way that the P waves and the S waves act as they travel through the Earth tell us about the inner core and the outer core. So let's take a look at what our P wave does. Let's look over here. So let's say right here is where our earthquake is generated. That earthquake is generated, those P waves are spreading out, right, like that ripple in the water, as I told you. Of course, we live on a round planet, so these P waves are not going to travel in a straight line, but they're going to travel in a curve. As you can see here, right, it's traveling in a curve. And it travels at a pretty consistent speed until we hit a layer in here. And what happens is this wave speeds up. And the reason why it speeds up is it's going through a higher density material. So what we see is when these waves travel through, that's an arrow up, high density, our waves speed up. There's just more molecules, there's less space in between the molecules, so it can move fast. When our waves hit a low density layer, they slow down, as you might imagine, right? There's more space in between the molecules, right, so it can slow down. So what happens, right, is it hits this layer and it speeds up, and you see that it bends it, right, because it's speeding up, so it's changing its path. So that means, let me change color here, everywhere in here, and if you were on the Earth, you would not receive P wave information. That's the P wave shadow zone. And if you know enough trigonometry, you can take the size of this arc, all right, project it backwards, right, and essentially get the size of the inner core. Now, if we take a look at what the S wave does, it does something different. The S wave, okay, as it travels through the Earth, it hits a layer and it stops. It just can't pass through it at all. So everything over here would be in the S wave shadow zone. If you remember, going back to the differences between the P and the S wave, remember the P moves the fastest, so it can travel through solids, liquid, and gases. However, our S waves can only travel through solids. So this is telling us, right, that once it stops, it's hitting a liquid. And if you remember back to the last chapter, our outer core is pure liquid and our inner core is solid. So when you take the size of this arc, right, project it backwards, you get a circle that's bigger than what we get from the P wave. So that tells us we have an inner and an outer core. So like I said, these seismic waves are really important because there are ultrasound inside the Earth. This is how we know where the other layers are as well, so let's just kind of take a brief look here. We call the spot where our waves our seismic waves either speed up or slow down. We call those discontinuities. So a discontinuity is saying my seismic wave is speeding up or slowing down. So the first discontinuity we see is the Moravec discontinuity, which is what we also call the MOHO. Okay? And the MOHO is located at the base of the crust, between the base of the crust and the upper mantle. So we're actually looking at that right here at that first line. So if you take a look, right, this red line is increasing at a steady speed, and then you see it jump all of a sudden. That's your change in speed, okay? So that's our MOHO, okay? Now what happens is the P wave velocity increases. So that's telling us that upper mantle is made up of more solid and dense material than the crust. Not more solid, just more dense. Then we hit the low velocity zone. As you can imagine, right, the low velocity zone we see here is the base of the upper mantle, and low velocity, that's telling us it's slowing down. And it's slowing down not because it's lower density, meaning it's lighter rock, because remember, the upper mantle is solid and rigid, whereas the lower levels of the asthenosphere, right, are partially molten. So as we get into that more partially molten material, our waves are going to slow down, right? Because remember, liquids allow movement in between the molecules, which means it's going to act like a low density material. As we get to lower levels, we have the 400-kilometer discontinuity. Here, our velocity increases. This is because we have some pretty cool minerals down there that are starting to become solid under high pressures. And then we have our last major discontinuity inside the asthenosphere, which is at 670. And at 670, our velocity increases again because we have some more minerals that are becoming solid there. Interestingly enough, we're going to talk about this number again in a little bit in the chapter because it's at this zone right here we don't see earthquakes really generated past that line. We're going to talk about that. Then we have our discontinuity at 290. Okay, so here we see the S waves stop and the P waves drastically fall. So this is our core mantle boundary, right? So here we're in the mantle. Oops, excuse my bad writing. And then here we're in the outer core. All right, so remember, our S wave stops, so we know we're in a liquid. Then our last one is where we hit that inner core, right? And of course, the velocity is going to speed up, right, as it hits that solid part of the inner core. So again, as I mentioned the last time, hopefully you see that these seismic waves are really imperative for understanding the structure of the inside of the Earth because they're like that ultrasound. All right, so from this point forward, now we're going to go and take a look at earthquakes and how, so we've seen how seismic's important. We're going to look at earthquakes and then also how earthquakes gave us clues to understanding plate tectonics.